Hello and welcome to ggplot2 and interactive graphics with R. This is section 1, getting started with ggplot2. With ggplot2 you'll be able to make beautiful publication-ready plots in a principled manner. Once you know the basic ideas behind ggplot2, you'll be able to design sophisticated graphics customized to your own type of data and analysis. In this section, we're going to take a look at setting up ggplot2 in RStudio, understanding the structure of a plot, mapping the data to graphical elements with aesthetics, understanding some subtleties with aesthetics, and using ggplot2 in scripts. In this particular video, we'll see how to install the free editor RStudio, which we'll use throughout this course, and how to install ggplot2 package. To install RStudio, simply go to rstudio.com, select the IDE for R, click on Download, and select RStudio Desktop. Download it, install it on your system, and once you have it installed, it should look like this. So this is RStudio. RStudio is made up of 4 panels. This is the console where you type in R commands. This is the editor where you write your script. This is the workspace, which is useful to see what variables are in use at the moment. And this panel here has the file system, plots that you'll be creating, and packages. And you see here in the list of installed packages that ggplot2 isn't available. So let's install it. Click on Install Packages. Type in the name of your package. So in this case, ggplot2. Click on Install. RStudio will install it automatically. It shouldn't take too long. You see here, RStudio is working and installing the ggplot2 package. This is done. You see here now ggplot2 does appear in the list of installed packages. So if you want to use it, we can just tick next to it. So now ggplot2 is loaded up in memory. So just to see if it works and to plot our first ggplot2 graph, let's copy and paste this ggplot2 command from the editor. So Ctrl-C, go back to the console, Ctrl-V here, and you should have this graph. Here, these bar charts. This is it. In this video, we've seen how to install the free editor RStudio and how to install ggplot2 package. In this video, we're going to take a look at the structure of a ggplot2 object. This object contains the necessary information for producing a graphic when it's rendered. The GG in ggplot is short for Grammar of Graphics. The main idea is that instead of having a single complicated function that draws a plot, you build up a plot from many smaller functions, just like combining words to form a sentence. Although the syntax differs from many other plotting languages, it makes your plotting code more readable and easier to debug. This can be disconcerting at first, but you'll understand it better as you follow along this video. Let's see a complete ggplot2 command. Most of the terms here are probably obscure for the time being, but let's ignore the details for now and concentrate on the general structure of the plot. Open activity0102.r in RStudio and run the code by highlighting the whole script. You can use Ctrl-A to select all line, and pressing Ctrl-Enter to copy it to the console. The first lines of the script call the library and prepare some data to be plotted. Here we randomly sample 1000 rows from the built-in diamond dataset. Head small show the first rows of our small dataset. Diamonds are described in terms of carat, price, shape, and so on. Let's decompose the ggplot2 command into a few elements. The first line, ggplot small, says that we want to create a ggplot of the small dataset that we just created. It's important that this argument is always a data frame. At this point, nothing will be plotted. Only the data has been set up, no drawing directives have been used yet. Next, geom_points tell ggplot that we want to add points to our plot. That is, we are creating a scatter plot. Geom is short for geometric object. We want to plot the carat variable on the x-axis, the price variable on the y-axis, and change the color depending on the cut variable. Notice that these instructions are wrapped inside the AES function. AES is short for aesthetics. Note that the plus sign joins all the commands together. This is how each layer is added to the object. Next, scale y log 10 tells ggplot to make the y-axis log scaled. Facet wrap splits the plot into several facets, that means several panels. ggtitle adds custom title to the plot. And by putting all these 5 commands together, we obtain the plot that you see on the screen. This is a general structure of a plot with ggplot2. Layers are added one at a time, each with their own specific logic. This will allow you to build very complex plots in a principled manner. Complex code for the plot is now clearer. Now we'll move on to the details of the command and the grammar behind ggplot2, in particular the concept of aesthetics and parameter. In this video, we're going to take a look at how graphical elements can be controlled by parameters called aesthetics. In ggplot2, the data is always passed on in the form of a data frame. The idea is to map the columns of the data frame to these parameters and use their type, for example continuous or categorical, to automatically produce the correct presentation. Let's see an example. Open activity 0103 in RStudio. Run the first 4 lines of the code. By doing this, we load the ggplot2 library and prepare a small dataset for future plotting. The dataset is a collection of diamond's properties, carat, cut, price, and so on. Some of these properties are continuous, for example carat, price, depth. Others are categorical, cut, color, and clarity, for example. Suppose we want to investigate the relation between carat and price with a scatter plot. For this, we use geom_point for plotting points on the graph. Run the first example. Here is how we did it. ggplot small creates a ggplot object and tells it to use some data, always a data frame. We then add a layer with geom_point. The code AES x is carat, y is price maps data to some of the properties of the geom, our geometric object. A point on the graph needs to have at least 2 properties, its x and y coordinates. Here, small dotted carat will be used for x and small dotted price will be used for y. This is all that is needed for producing the plot. Note how the labels are automatically produced and the plot has nice default colors. Run example 2. This is similar to the previous plot, but this time each point has a color that depends on the value of the cut of the diamond. Note that since cut is a categorical variable, that is a factor in our terminology, ggplot has automatically decided to use a discrete scale for the color scheme. Also, you notice that the color scale appears automatically on the graph. If the data or the number of cuts changes, the graph will change accordingly, but you won't need to update the code, since all the graphical elements are a function of the data. We've seen how to link the data to graphical elements through the use of aesthetics and how the type of data, either continuous or categorical, is automatically used by ggplot2. In the next video, we will clarify some subtleties about aesthetics, which can be a bit puzzling at first sight. In this video, we're going to see how aesthetics work in more details. In particular, we're going to see how aesthetics can be defined in the first call to ggplot, and how aesthetics can be set to a constant value rather than mapped from the data. A typical error when learning ggplot2 is to mix the concept of mapping and setting aesthetics. We clarify these 2 concepts in a simple example in this video. Open activity 0104 and run the first 4 lines to prepare some data. Then run example 1. The aesthetics, x, y, and color are defined in the call to ggplot, so you don't need to specify them again in geometry since they're already available. Now, run example 2. In this example, only the aesthetics x and y are defined in ggplot. But note that the aesthetics color is defined in geometry. The two plots are identical. This is useful for sharing aesthetics among geometric objects. You can think of it as defining a global variable in the call to ggplot, which can then be accessed by all geoms. Rather than having a map from the data to graphical properties, we can also set graphical properties to a certain value. To do this, we simply set them outside the call to AES. Run example 03. The color is now defined outside the aesthetics to be a constant value. What would have happened if you had defined the color within aesthetics? Run example 4. As you can see, this is not what we wanted. The points are colored in red rather than expected blue. What happened is that because the color was defined to a constant value within AES, ggplot understood this as a map from the data to the aesthetics. But in this case, the data consisted of only one value, the string blue, and therefore were translated to the first color of the default color scheme, in this case red. If you see this kind of unexpected plot, you know now where the error comes from. We've seen that when you define aesthetics in the call to ggplot, they are shared by all geoms in the plot. You can also define aesthetics for individual geoms. When aesthetics are defined inside the AES call, ggplot assumes that they refer to mapped variable. If they are defined outside the AES function, then they are assumed to be constant. In the next video, we will see how to use ggplot in scripts rather than in the command line as we've done so far. In this video, we will see how to use ggplot2 in a script rather than in console. So far, we use ggplot using one-liners in the console. This is obviously not sustainable if you want to make more complex graphs and use them in scripts. Open Activity 0105 in RStudio. Run the first few lines to prepare some data. As we have seen before, a plot is made up of different layers. We can store the ggplot object in a variable, say p, and keep on adding to it. Highlight the first line of example 1 and run it. By running the first line of example 1, we create a ggplot object, define some data, and the aesthetics x and y, and store the object in a variable p. We can now use this object for other plots. Run the second line of example 1. You will get the black and white scatter plot that corresponds to the ggplot commands we set by adding the geopoint layer to the object p. Likewise, run the third line of example 1. The colorful scatter plot corresponds to the ggplot command we set by adding the geopoint layer with the extra color aesthetics to the object p. By storing the ggplot object into a variable, we don't need to rely on one long line of commands, but we can build very complex graphics one layer at a time. Now, clear all the plots by clicking Clear All in the Plots panel. Click on Source in the editor to run the code as a script, rather than running it in the console. As you can see, none of the plots appear. The reason the plots were actually produced and appearing when running the console is that by typing the ggplot command, we implicitly printed the object, the same way you see the value of a variable when you enter its name in the console. To produce the plot from a script, and see it appearing on the screen when you click on Source, you need to make the call to print explicit. Change p plus geopoint to print p plus geopoint. Save and source the script. You now see the graph appearing on the screen. In fact, the plot will only be built when a call to print is made. You typically build complex graphs rapidly and have the slower rendering process happening only when required. We have seen how we can gradually build complex ggplot objects by storing them in a variable, rather than using long one-liners. We also saw how to produce graphics from a script rather than the console. In the next video, we will learn how to use geomline to draw lines very easily. Hi, in this section of the course, we will take a look at basic plots that often come up during data analysis: lines, paths, bar charts, histograms and density plots, box plots. In this video, we will learn how to use geomline to make lines very easily. So far, we have only plotted individual data points on scatter plots using geom points. It often makes sense to connect data points, for example body temperature over time. Lines can also be used for visualizing two continuous variables. For this, we're going to use geomline. In RStudio, open Activity 0201. Run the first few lines in the console up until head X. On the screen, you'll notice that we have a sample data set created from a recording of stock market values, EU stock market. This is a data frame with three columns: index, an index which increases with time; stock, the name of the stock; and value, the value of the stock. We have also removed 200 rows at random and shuffled the indices. We use the aesthetics color to differentiate between the stocks. Geomlines require at least two aesthetics, X and Y. It will connect the point along the coordinates with a line, but will also make sure to sort the value for X in increasing order. We see that despite the indices having been shuffled, the points are arranged in a correct time order. Lines are always drawn from left to right. They never zigzag across the plot. It automatically produces a legend on the graph. Run the second example. In this case, all the data points are joined up, since we didn't give ggplot any information as to how to differentiate between them. This is obviously not terribly useful. Run the third example. In this case, we use the aesthetics group in order to separate the four different stocks. In this video, we've seen geomlines, which allows you to connect data points in a graph, which is especially useful for time series or for visualizing the relation between two variables. In the next video, we'll see how to draw paths. In this video, we're going to take a look at how to draw another type of line called a path. We've seen how geomline connects data points from left to right by first sorting the X aesthetics. Sometimes the order of the data points is important, for example when tracking the movement of an object in the plane through time. For this, we need to use geompath, which we look at in this video. Geompath works in a very similar fashion as geomline, but connects the data points in the order in which they are presented in the data frame, so there's no sorting going on. Open Activity 0202 in RStudio. Run the first few lines in the console until head migratory zebras. The data contain the location of 6 zebras over a period of time in northern Botswana. Run the rest of the code in the console. Geompath will connect each data point with a line, in the order they appear in the data frame migratory zebras, whose rows already been sorted by time. Each zebra is associated with different color thanks to the aesthetics color. You can see the meandering routes zebras have taken over a period of time. Using geomline instead of geompath will not be appropriate in this context. P plus geomline first sorts the data points by latitude, because it is mapped to the aesthetics X, which is nonsensical. Zebra can go back and forth the same latitude at different points in time. We know now how to draw lines and paths using geomline and geompath, depending on the station we're in. In the next video, we will see how to make bar charts. In this video, we're going to see how to use bar charts for comparing quantities. Bar charts are used for comparing single values across subsets of data. For example, the number of items in a few subsets, the mean value of the number of populations, etc. Open Activity 0203 in RStudio. Load ggplot2. We'll be using the diamonds dataset to plot how many diamonds we have for each value of cut and clarity, two properties of diamonds. Run the first example. We can see that we have about 5,000 diamonds of good cut, 12,000 diamonds of very good cut, etc. We don't have to specify the height of each bar, because by default they are calculated as the number of items in the subset defined by the aesthetics X, which in this case is cut. You can map the height of each bar to a value of your choice with the aesthetic Y. You also have access to other aesthetics. Fill, for example, it controls the color of inside the box. For example, if you want to map it to clarity, the bars for each value of cut are broken down into a set of smaller bars, one per value of clarity, as in example 2. However, bar heights are now difficult to compare because they don't start from the same height. Use the parameter position and set it to dodge to put each bar on the same baseline. Run example 3. Each bar now represents the diamonds for particular values of cut and clarity, and they are easy to compare because they all start from the bottom line. In this video, we've seen how to quickly produce bar charts and control their relative positions or comparing them more easily. In the next video, we'll see how to draw histograms and density plots. In this video, we'll take a look at histograms and density plots for visualizing the distribution of the data. It's often interesting to visualize the range and the most frequently occurring values of your data. For this, we can use histograms or density plots. ggplot2 offers both of these options. Let's see a few examples. Open Activity 0204 in RStudio. Run the first 2 lines of the code. We'll be using the diamonds dataset again. Type $diamond in the console if you want to know more about it. Let's see what is the distribution of diamond prices in the dataset. Run example 1. Geom histogram has one required aesthetics, X. The range of values for X will be divided in equally sized bins, 30 bins by default, and the histogram shows the number of rows for which X falls into the bin, here the price of the diamonds. This gives us a clear picture of the range of values spanned by the price of a diamond. For example, most diamonds cost less than $5,000, and most expensive diamonds are rare. If you add all the bins together, you'll find the total number of diamonds in the dataset. You can easily change the number of bins with bin width. For example, bin width is 100. Note that we have also used the aesthetics fill to get a separate histogram for each value of cut. If you have a large number of data points, you can use a density plot instead. The density plot does 2 things. It smoothes out the distribution, and the area under the curve sums to 1, so it's easier to compare distributions even if they don't have the same total number of items. Doubling the number of items doesn't make the curve twice higher. Run example 3 to see the results. Using geom density instead of geom histogram made the presentation of the distributions smoother on the eye. You should only use density plots when you have a large number of items. The smoothing can lead to misleading artifacts, bumping up the values of low frequency. The distribution of diamonds of ideal cuts masks the other distribution. We can make the coloring slightly transparent by using a parameter alpha, a number between 0 and 1, from completely transparent to completely opaque, as in example 4. We've seen how to use histograms and density plots for visualizing the distribution of a quantity. In the next video, we will see how to represent the data more succinctly with boxplots. In this video, we will see how to use a common statistical plot, the boxplot. Histograms and density plots show us the whole distribution of a quantity. They take a lot of space and can be difficult to compare the more distributions you have. Boxplots have less information but are more concise, so you can compare lots of them easily. Open Activity 0105 in RStudio. Run the first few lines to load ggplot2 and display some numerical information about the dataset. Run example 1. The graph shows the distribution of the price for each value of cut in the form of boxplots. The middle bar of the boxplot is the median value. 50% of the prices are below this quantity, 50% of the prices are above it. Bottom and top value of the box are the 25% and 75% quartile. The whiskers represent where rarer values would lie. Dots are extreme points or outlier. Box plots are very good for summarizing a dataset with a few numbers. They can give an impression that the distribution has one single peak. It is good practice to check whether this is the case, for example, with the density. You can add an extra piece of information to the box plot with the parameter notch, which indents the box around the median. This is used for comparing two box plots. If the notches don't overlap, the two medians are very likely to be different. Add a notch to the previous plot with notch is true. For example, diamonds of fair and good cuts have very close medians, but since the notches don't overlap, their difference is statistically significant. As with any other geo, you can change many more aesthetics. For example, you can map the filling color with fill. If we map it to clarity, a property of the diamond, we can compare the price of diamonds on the basis of their cut and clarity. Run the third example. You see that now we can easily compare 40 distributions in one graph. We've seen how to use box plots to summarize and compare multiple distributions. In the next section, we will see how to use group and color and other aesthetics for conveying more information in a graph. In this section, we will see how to use more aesthetics to add extra information to a graph. In this video, we understand about the group and color aesthetics. When we have two variables to visualize, we can use the x and y coordinates to represent the data. For a third variable, we can use color. Remember that in ggplot terminology, these are all called aesthetics. For visualizing more than 3 variables, we just need to add more aesthetics. So far, we have only used color as an aesthetics to differentiate between data points. We can use more aesthetics simultaneously, for example group and color, to convey more information. Open activity 0301. Run the first 10 lines to load ggplot2 and get a first view of the data. The chick weight data contain information about the growth of chicks under different diets. As you can see, we have from 10 to 20 chicks assigned to each of the 4 diets. A line connecting the weight over time for each chick is appropriate, so we'll be using geom-line. But we also want to differentiate between the diets. For this, we map the diet to color and an individual chick to group. The aesthetics group is used for connecting the data points when used with geom-line. Let's run the ggplot command. This way, each chick has its own line, and each line is colored according to the chick's diet. As usual, we also get the default legend for free. You can convey more information by mapping multiple aesthetics at once. As you've seen, the aesthetics group is useful for collecting data points in different subsets of the data. In the next video, we'll look at using another aesthetics, size. In this video, we're going to go through another example of using multiple aesthetics, this time the size and the color of points and lines. With ggplot, it's easy to map the data to multiple graphical elements in order to visually convey more information about our dataset. We're going to use size and color to add 2 extra dimensions to our graph. Open activity 0302 and run the first 2 lines. MPG contain a few attributes, manufacturer, consumption, etc., about a number of cars. Let's start with a simple plot. What is the consumption in miles per gallon in city versus on highway for all the cars in the dataset? Run the first ggplot command. Let's add information about each car's manufacturer and the car's engine displacement. One way to achieve this is to map the manufacturer to the color of each point and the engine displacement to its size. The bigger the point, the bigger the engine displacement. Run the second ggplot command. We now have much more information than in our first graph. We can read a car's consumption in the city and highway, along with its manufacturer and its engine displacement in one single. Both mappings automatically produce legend. The default colors are chosen so as to be as distinguishable as possible and of similar likeness, to avoid some colors to stand out. However, as in this case with only 15 categories, colors are quickly difficult to differentiate. We have covered how easy it is to add extra dimensions to our graph by mapping multiple aesthetics at once. In the next video, we look at how to minimize overplotting, which happens when multiple data points fall in the same location on the graph. In this video, you'll get the solution for plotting many data points that could mask each other. With a large dataset, or with many data points having the same value, the resulting graph can be misleading because it doesn't convey the true number of data points plotted. Graphical elements will hide or mask each other. This is called overplotting. We're going to see how to slightly jitter points to minimize overplotting. Open Activity 0303 in RStudio. Run the first 9 lines of the code. Notice that with nrow mpeg, we're expecting 234 data points to appear on the graph. We plotted the consumption in city and on highway for each of the 234 cars in the dataset. How many data points do you see on the plot? Certainly fewer than 234. This is because the reported consumptions have limited number of values, so cars having the same values for both city and highway end up on top of each other. To minimize this, we can use the parameter position with the function positionJitter to randomly jitter the points. Let's see how this is done. Run the second ggplot command. With positionJitter width is 0.1, we randomly move each point by a small amount horizontally. The amount of jittering should be moderate, otherwise the position of the point will be so different from the original value that the graph will be misleading. You can also use the aesthetics alpha to make the point slightly transparent so that they cannot hide each other. Set it to a number between 0 and 1, with 0 being completely transparent and 1 being completely opaque. We can now see most of the 234 points and have a better sense of how many cars are represented. We saw how to use position jitter to avoid overplotting by randomly moving the data, but without producing a misleading graph. In the next video, we'll see how to easily generate plots for subsets of the data. In this video, we will see how to automatically produce individual plots for each value of one variable. It is always possible to draw a whole dataset on a single graph, but it's often more informative to look at subsets of it individually. With faceting, it is very easy to produce a similar plot for multiple subsets of a dataset. Open Activity 0304 and run the first 9 lines. We have plotted the distributions of the price of 50,000 diamonds for each possible cut, from fair to ideal. This can be useful to compare one with another, but the plot is rather difficult to read if you're interested in each distribution individually. What we want is a plot of price distribution for each value of cut. We can do this easily with the facet function. Run the second ggplot command. With very little change to the code, we produce 5 individual graphs, one for each value of cut. All the panels share the same axis. This makes it easier to compare values across panels than just drawing 5 separate plots. It's also much more space efficient. You can also control the plot's layout and axis with options like ncol, nrow, and scales. Use $facet wrap for the complete list of options. Now, we can automatically produce individual plots for each value of a particular column in the data frame. This makes for less crowded and more legible graphs. In the next video, we will see how to make subplots for each values of several variables. In this video, we're going to see how to generate plots for each value of several variables. With a large enough dataset, it's often interesting to look at subsets defined by several variables. We're going to see 2 ways to make conditional plots over 2 variables. Open Activity 0305 and run the first 11 lines. we end up with a graph similar to what we had in the previous video, the distribution of the price for different types of diamond. By using facet wrap color tilde cut, a plot is produced for each of the combinations of color and cut, which is what we want here. However, as it is difficult to appreciate what is the importance of cut on the price distribution, because the plots are simply strung one after the other. Run the second ggplot command. We have used facet grid instead of facet wrap, which produces a more orderly table of graphs that makes for easier reading. The two variables cut and color now run on the x and the y-axis. It is possible to use more than two variables by using the formula in the usual way, for example color tilde cut plus clarity. You can also add extra plots with all the data by setting the option margin to true. See the help file for facet grid to see the complete list of options. From this video, you have learned that faceting with several variables is possible with either facet wrap or facet grid, but the plots resulting from facet grid are easier to interpret. In the next section, we will see how to use a statistical summary in our plots. In this video, we're going to see how to uncover trends in the data from scatterplot using built-in R functions. A scatterplot can give us a good idea of the relation between two variables. You can easily add trends calculated from the data to the scatterplot and make the trend stand out. ggplot supports two types of smoothing, linear regression and LOES, which is a non-parametric model which can accommodate more complicated trends. Open activity 0401 and run the first 9 lines. The plot shows the chick weight data we came across before. The weight of 50 chicks under 4 different diets was monitored for a period of time. The plot is a bit confusing because all the data is there. Using geomsmooth, we can summarize the effect of each diet and thus get 4 curves instead of 50. Each curve will capture the underlying trend for each diet. Run the next ggplot command. Geomsmooth builds a polynomial fit to each of the diets. The gray area represents the standard error on the best fit line, so the better the fit, the thinner the gray ribbon. The optional parameters, alpha and size, control the ribbon's transparency and the line thickness, respectively. Geomsmooth uses LOES by default if there are fewer than 1000 points, as it is the case here. By using the parameter method in Geomsmooth, you can get a linear model instead. Run the next ggplot command. This time, the trend is forced to be linear, that is, a straight line. We have seen how to use Geomsmooth to quickly view trends in the data where many individual lines are too confusing, and also visually appreciate the fit of the model. In the next video, we will see how to fit more sophisticated curves to the data. In this video, we'll carry on investigating different ways of uncovering trends in our data, this time with polynomial regression and spline. The data used here has to be sufficiently complicated such that no obvious model comes to mind. However, it is still helpful for the plot to show trends in the data. We'll use 2 ways of summarizing the data in order to uncover possible trends. Open activity 0402. We'll use the chick weight dataset again. Run the first ggplot command. By using the formula y tilde poly x, 2, we are fitting a polynomial model of degree 2. The higher the degree of the polynomial, the wigglier the line can be. Another way to smooth the data and uncover possible trends is to use splines. Splines connect data points piecewise as smoothly as possible. They can accommodate very complex shapes. Run the next ggplot command to see the effect of spline. The formula is y tilde ns x, df is 3. The function ns comes from the package splines and will produce the splines. We are not limited by the range of functions offered by ggplot2. The parameter df, or degrees of freedom, controls how wiggly the curve is. More methods are available. Just run the last ggplot command for a few extra examples. The data points in the graph are the black dots. We use SC is false to hide the gray ribbon and only show the trends. Have a closer look at them in your own time and experiment with your own function. We saw alternatives for graphically summarizing the data using any models of your choice. In the next video, we'll see how to plot any user-defined function. In this video, we're going to see how to add a user-defined function to a plot. Rather than fitting a model, you might want to plot a particular function to compare your data against. For example, to check that the data is behaving in the manner you're expecting. With stat function, you can draw any function you want, as well as passing parameters to it. Open Activity 0403 and run the first ggplot command. We took a large sample of 1000 normally distributed variables and plotted its distribution. We then added a plot of the theoretical normal distribution with dnorm using stat function. We can visually check that the sample is large enough and the distribution is very close to its theoretical value in red. Run the next command. The data frame sum averages contain 1000 averages of samples of 10 uniformly distributed values. An important theorem in statistics, the central limit theorem, tells us that the averages should be normally distributed with a predictable mean and standard deviation. The next ggplot command helps us verify that this is indeed the case. We're adding dnorm to the plot again, but this time with some extra parameters, mean and SD, specified as a list in the parameter args. The theorem gave us the predicted values for the mean and the standard deviation. You can find the derivation in the source code. You can see a good fit between our data and its theoretical distribution. Now you know that it is very easy to draw a function on top of a plot with stat function. This is very useful to check an assumption about the data, for example. In the next video, we'll see how to plot very large datasets efficiently. In this video, we're going to install and use BigViz, an R package specially designed for large datasets. If you have a very large dataset, for example hundreds of thousands of rows to millions, it makes little sense to try and plot all the data on the screen. There's not even enough pixels. We're going to use BigViz to pre-process and summarize the data before plotting it. We first need to install the package. It's not on CRAN, but on GitHub. But it is easy to install in a couple of lines. Open Activity 0404 and run the first two commands. Now that the package is installed, you can comment out these two lines. You won't need them anymore. Next, we load the necessary libraries, ggplot2 and BigViz, and have a look at the data we'll be using. The dataset MyMovies contains information about films and has more than 130,000 rows. Let's plot the distribution of movie length versus rating. Run the next two lines. BigViz creates a heat map, a two-dimensional distribution, and typically works like this. First, you put your data into bins, just as when you plot a histogram, for example. The bin function will automatically find a good bin width for your data. You can also specify a bin width with the parameter width. Next, you condense or summarize each bin. This creates a condensed object from a list of bin data, which only contains the location of each tile in the heat map and its value, that is, a count. MyMovies summarized can then be plotted quickly since it only contains the pre-processed data necessary for the plotting. Run the ggplot command. ggplot2 was able to plot the large dataset very quickly. We've seen how to quickly plot a very large amount of data thanks to the package BigViz, which produces a summary of the data. BigViz is partially written in C++, which makes it process the data very fast. In the next video, we'll see how to smooth the plot and remove outliers. In this video, we're going to look at two other important features of BigViz: smoothing plots and peeling data. A very large dataset is bound to contain extreme values, which can lead to a distorted and misleading plot. We're going to see how to automatically remove outliers and how to smooth the original plot. Open Activity 0405 and run the first three commands. We'll be using the movies dataset again. We bin and condense the data as before, but note how we've not manually removed extreme values this time. Let's plot the summarized data by running this code. Because of a few movies with extreme length, more than 300 minutes, the plot is squashed on the left-hand side and is difficult to read. Data points with very rare values are usually considered outliers. The function peel removes regions with very low density, that is, very isolated points, therefore likely to be outliers. By default, peel keeps 99% of the data. You can control this cutoff point with the parameter keep. The advantage of using peel over a manual selection is that the cutoff point is chosen in the context of the whole dataset. Run the second portion of the code. The plot is now more informative. Next, we apply smooth to decrease the ruggedness of the original plot. In the same manner we used geom_smooth in the previous video, we want to ignore noise to find trends. The parameter h controls the size of the kernel for each dimension, that is, the amount of smoothing applied. Recall that .count is a column of MyMovieSummarize created during the condensing process. We now have a nicer looking plot, which is easier to read because of unimportant local differences have been ironed out. We've used two functions from the package BigViz to automatically remove outliers and smooth the original plot. In the next section, we'll see how to customize our plots. In this section, we will see how to override the choices made by default by ggplot2 and customize our plots. In this video, we will see how to control axes for plotting on different scales or changing the area to be plotted. It is often useful to transform the data before plotting it, in order to make a relationship more apparent. Typical transformation is taking the log of the value to produce a log or log-log plot if both axes are transformed. Open Activity 0501 and load ggplot2. Using our usual diamonds dataset, we want to plot carrot versus price on a log-log scale. A simple way to achieve this is to directly transform the data and replacing price by log10 price and carrot by log10 carrot. Run the first example. We see a very clear linear relationship on the log-log scale, which suggests that the price is the carrot with some exponentiation. However, the axes are difficult to read. Reading 3.5 on the y-axis, for example, means a price of 10 to the power 3.5, which is 3,125. Using scale x log 10 and scale y log 10, we can ask ggplot2 to transform the axes without us applying the transformation manually. Run the second example. This way, we haven't manipulated the data, and it's much easier to read the values of the axis. You can also control the limits of your plots with xlim and ylim. Run the next example. This is a distribution of movie length from the dataset movies. Because some rare and very long movies, most of the data is squashed on the left-hand side. Use xlim to only plot the distribution between 0 and 3 hours. Run the last example. We are now looking at the more interesting portion of the distribution. We saw how to plot on different scales and to plot only parts of the graphs without manipulating the data, using scales and limits. In the next video, we'll see how to control the order in which categorical variables are plotted. In this video, we will see how to control the order in which categorical values are plotted. By default, categorical values are ordered by their level, if they're already a factor, or in alphabetical order if no level has been defined. This is not always desirable, and there's a way to change this. Open Activity 0502 in RStudio. We first build a small data frame to plot. It shows the proportion of different modes of transportation to commute to work in the UK. We first make a bar plot directly with this data. The categories appear in alphabetical order: car, cycle, other, public transport, and work from home. Note the order in which the dataset was defined. Since ggplot2 uses the factors level to order the categories, we need to specify the levels to control the order. Changing the levels implies changing the data, so as a precaution, we'll make a change on a copy. In this situation, we want the categories in alphabetical order and with other on the right-hand side. We define new column, user-defined, where we specify the levels explicitly with the function factor. Using user-defined instead of categories in the aesthetics, the bars are now ordered exactly like we want. You can also define the order more programmatically, for example to order the categories in the order they appear in a dataset. In this case, the levels are defined as the values appear in the vector commute $categories, hence respecting the original order. In this video, we've seen how to control the order of category variables in a plot. In the next video, we will see how to change the default color palette when plotting categorical variables. In this video, we'll see how to override the default color palette and make our own. The default colors for a categorical variable are chosen by picking up evenly spaced hues and keeping luminance and chroma constant. Let's have a look at a simple plot. 8 colors for 8 categories are automatically chosen by default. You can see the color progression from orange to brown to eventually pink expected by going around a color wheel. This is a simple enough system that gives good result. If you have a good idea of the color scheme you're after, you can use scale something manual, with which you spell out the color for each value of your categorical variables. Scale color manual will override the palette for the color aesthetics, and scale fill manual will override the palette for the fill aesthetics. Run the next example. Colors can be defined by name, red, blue, etc., or by the RGB code. Choosing a palette is actually fairly difficult. Scale Color Brewer and Scale Fill Brewer offer a good collection of palettes that have been carefully designed to give good contrast on geographical maps. You can see them in action on the website colorbrewer2.org. There you can choose between sequential, diverging, and qualitative palettes and see their effect. The website also tells you whether it is suitable for a colorblind audience. We use the palette Set1 of type qualitative from colorbrewer2.org for our plot. The colors chosen have very sharp contrast and are very distinctive. In this video, we've seen how to control the color palettes for categorical variables. In the next section, we'll see how to override the default palette for continuous variable. In this video, we'll see how to customize the color palette for continuous data. By default, ggplot2 uses a gradient from black to blue for coloring continuous variables. You might want to use a different gradient or even more than 2 colors to visualize different value bands, for example. Open Activity 0504 and run the first example. We're plotting the diamonds dataset with carat versus depth. The color is a function of the price. Instead of the usual black to blue gradient, we might want to use, for example, yellow to red. To change the gradient, use Scale Color Gradient. The parameters low and high control which colors you want to use. You can also use the parameter limit to focus on a specific band of values in your data. For example here, we decide to only look at prices between $5,000 and $10,000. We can do that without having to subset or modify the original data. The gradient now goes from yellow to red and for prices from $5,000 to $10,000, as we wanted. Data points not in this range are shown in gray. Use the parameter na.value to change their color to another, or set it to na to make them invisible. It only affects the plot, not the data. You can also use multiple gradients. For example, Scale Color Gradient 2 asks for an intermediate color to go through. Suppose we want to visualize whether a diamond has a price below or above average. We can use a first gradient from red to white for diamonds below the average price, and a second gradient from white to blue for more expensive diamonds. For this, we set the parameter midpoint at the average price. We could change the colors by using low, mid, and high, but they already had red, white, and blue by default. As an extra, we also use the parameter trends to define the gradient on a log scale. It is more appropriate here because a $100 difference between cheap diamonds is not the same as a $100 difference between expensive diamonds. We see which diamonds are below and above average very easily. For example, from 1 carat onwards, diamonds are more expensive than average. We also see how the log scale automatically appears on the color guide. In this video, we've seen how to override the default palette for continuous variables and achieve interesting effects. In the next video, we'll see how to customize non-data elements like legend title and labels. In this video, we'll see how to customize labels, legends, and axis directions. By default, axis labels and legend titles are given by the column names corresponding to the aesthetics. This is not always desirable, because they can be cryptic to read or unsuitable for a publication. Open Activity 0505 and run the first example. We have plotted the city and highway consumption for 50 cars from the MPG dataset. The legend title for the transmission type is trends, which is a bit cryptic, as well as the axis labels CTY and HWY. Changing the axis labels is easily done with xlab and ylab. Adding xlab city miles per gallon and ylab highway miles per gallon to the plot modifies the labels. Changing the legend titles can be done with the parameter guide in the color scale function used for generating the palette, or by using the aesthetics name in the guides function. Both solutions will override default values. The function guides actually gives you a lot of controls over the rendering of the palette, from its legends to its position. Follow the links in activity0505.r to see more examples. It is often useful to flip the X and Y axis for better visualization. Rather than swapping the aesthetics X and Y, we can simply use chord flip to achieve the same effect. Here is a usual bar chart flipped over to have the car manufacturer's name more readable. Note that the effect is purely graphic. The list of cars manufacturers goes from Audi at the bottom to Volkswagen at the top, because it was originally going from Audi on the left to Volkswagen on the right. To start with Audi at the top, see video 2 in this section, or the last example in the current script. In this video, we saw how to override axis labels, legend titles, and axis direction. In the next section, we'll see how to build interactive graphical web pages from R with the package Shiny. In this video, we're going to introduce the R package Shiny for easily creating interactive web pages from R. You'll see how you can use R to produce interactive graphs in a web page, which can then be used with any browser, making it easy to share even with people who are not familiar with R. The overhead of turning static graphs into interactive graphs is negligible considering what you get in return. Before we dive into the details of Shiny, let's run an example. First, we need to install Shiny. Open R and run the command install packages Shiny, or use the install package button in the package panel. You only need to do this once. Next, let's run an example. Open Activity 0601 and load the package and run the Shiny command. By running the example, we have created a small local web server which hosts our interactive web page. A web browser opened with an interactive histogram. The graph changes as you move the numbers of samples on the slider from 1 to 1000. On top of the interactivity, which we didn't have before, the advantage of a web page is that anyone with access to this page can use it, even if they don't have R installed on their machine. To stop the server, go back to RStudio and stop the command by using the stop button. In this video, we have installed the R package Shiny and saw it generating a web page with an interactive graph written in pure R. In the next video, we'll learn the structure of a Shiny app. In this video, we're going to study the structure of a Shiny app and see how each part of the structure interacts with the other. If we want to build our own complex interactive web pages, we need to understand how information is passed on from the browser to the R code and back. For this, we need to know how a Shiny app is structured. Open RStudio and make sure you are in the folder section 6 with either getwd or by looking up the path at the top of the console. You can change your working directory from the console with the command setwd, or you can also use the Set as Working Directory button in RStudio from the Files panel. Run the following command in the console: library shiny run app activity _06 _02. This is the example that we saw in the first video. Let's stop the server and see the code that generated this page. The code sits in the folder activity 0602. The argument for run app is the name of this folder. Shiny apps always consist of at least two files, which are named ui.r and server.r. As the names suggest, ui.r, for user interface, contains the code for what appears on the web page, the text, the plot's location, and the controls, while server.r contains the code that generates and updates the content of the web page, the graphs, and the results of the calculation. Look at ui.r. The code consists of a single call to Shiny UI. Page with sidebar provides the general layout of the page, a header, a sidebar on the left-hand side, and the main panel. It produces a modern and lean web interface. Header panel sets the page title, and sidebar panel adds some control in the sidebar. The main panel is populated by a single plot output. Now let's move on to server.r. Server.r consists of a single call to the function ShinyServer. ShinyServer always has two arguments, named input and output, which are lists. The information from the page is passed on to the server via the properties of input, for example, input $obs. In return, the server returns its result, graphs or text, via the properties of output, for example, output $displot. The names of input's properties are given in the call to the controls in ui.r. Input $obs in server.r comes from slider input obs in ui.r. Likewise, output's properties in server.r connect to the rendering function in ui.r. Output $displot in server.r is fed to plot output displot in ui.r. In this video, we briefly saw how Shiny works. A file, ui.r, sets the web page layout, while a second file, server.r, computes the content. They communicate using two lists, input and output. We'll learn more about this process later when we study reactive programming in video 4. In the next section, we'll see how to generate textual content on a web page. In this video, we're going to see how to generate textual content on the web page. It is often useful to show textual information to the user, for example a table of values or some statistics. Launch RStudio. Go to the folder section 6 and type in a console library shiny run app activity _06 _03. Choose a dataset and number of observations to see the content changing. You can see three types of textual outputs in this page. Free text, formatted text, as you would see it in the console, for example, and a formatted table. Open ui.r and server.r in the editor. In the previous video, we saw the functions plot output in ui.r used together with renderplot in server.r, which was used for sending a graph to the web page. This time, we use text output in ui.r together with render text in server.r to display free text. The expression in render text must be anything that can be passed to the R function cat, typically a string or a vector of strings. Note that the property of the output in server.r, introduction, matches with the argument of the text output in UI.R. To capture the content of the console, for example the output of a function, we use verbatim text output in UI.R, together with renderPrint in server.R. For tables, you need to use a combination of table output in UI.R and render table in server.R to generate a formatted table from a data frame or a matrix. In this video, you have seen how to generate and display textual content, either as free text, formatted text, or in a table, by using three different pairs of functions: render text and text output, render print and verbatim text output, and render table and table output. In the next video, we'll see in more details how Shiny works with reactive programming. In this video, we're going to have a closer look at reactive programming, on which Shiny is based. To program interactive graphics, you need to write some code that is executed only when some change occurs. Using Shiny's concept of reactive programming, you'll see how to tackle this. With Shiny, you only need to declare an expression as reactive for it to automatically pass messages between the UI and the server. You don't need to write all the necessary code. Shiny does it for you behind the scenes. Open RStudio and run the Shiny app activity 0604. So write library Shiny, run app activity 0604. Entering some text in the text box updates the content of the first text area automatically. Selecting a dataset in the menu updates the second text area. Note how every time you select a dataset, a new random value is shown in the first line of the text area. Changing the value of the text box updates the first text area only. The random value doesn't change, because it hasn't been recalculated. Only the parts that depends on changes in the UI are updated. Shiny doesn't waste time updating everything. Let's look at the code. The function renderText and renderPlot are reactive, that is, they listen to changes to input. Consider output $DataSummary. The expression depends on input $dataset, which comes from the drop-down menu in UI.R. Any change in the menu will affect the expression, which will change the value of output $DataSummary, which will in turn be reflected in the web page. This can be represented by this diagram. You set the connections between the input and the output, but all the message passing is done for you automatically. You can write your own reactive expressions. Uncomment the following code in the body of Shiny server. The expression listens to input $dataset. You can use it for output $DataSummary and have the changes cascading from one reactive expression to the next. Reactive functions are especially useful to pass on process values to multiple outputs. Replace get input $dataset by get my reactive expression. Note that you need the two parents after my reactive expression because it is a function. Your code can be represented by this diagram. Output $DataSummary now listens to my reactive expressions, which in turn listens to input dataset. Run the app. It works just the same. You could have defined my reactive expression as a normal function. The app would have run just as well. However, it is more efficient to declare functions as reactive when they depend on changes in the user interface and are used by multiple functions. This is because reactive functions save the latest calculated values and can avoid repeating their calculations. Consult the Shiny tutorial for more details about the inner workings of reactive programming. In this video, we have seen in more details how information is passed on from the web page to the server and how Shiny only updates what is necessary. In the next video, we'll see what strategy to apply when regenerating the web page after any change would be too slow. In this video, we're going to see how to use a submit button to send the content of the form to the server. If your graph requires a substantial time to be calculated, updating it as soon as the control is modified will result in poor user experience. Shiny offers a submit button, which sends the content of the form to the server only when it's pressed on. This way, all the changes will be sent to the server in one go, when the user is satisfied with them. Open R and run the command line library shiny, run app activity 0605. The graph shows the distribution of the diamonds broken down over two of the diamond's properties. Notice how selecting properties does not update the graph immediately. The user has to click on the button Refresh the graph for the plot to be regenerated. Look at the source in R. The button is added to the sidebar with Submit button and the text. Server R does not have a reference to the button. Although the plot depends on input first property and input second property, the expression will only be evaluated when the button is pressed. In other words, the button acts as a delay mechanism, which prevents the propagation of the changes until it's pressed. We use ggplot2 to create the graph. In this case, we have to explicitly print the ggplot2 object in order to return a graphical output. As usual with ggplot2, graphs are rendered only when they're printed. In this video, we saw how to use a submit button to avoid updating the results too frequently. This is especially useful if the computations take a substantial amount of time. In the next section, we'll learn more about the interactive controls offered by Shiny and how to publish your work. A web page can be composed of semantically different elements that can make it complicated and crowded. In this video, we're going to see how to use tabs for visually separating different parts of the main panel. If your data is complicated and you have a significant number of results to show on the page, it's a good idea to group them in separate tabs. Tabs in Shiny are very easy to set up. Let's have a look at one example. Open RStudio, make sure you are in the folder section 7, and run in command line library shiny, run app activity 0701. We see two tabs, each with their own title and content, distribution and averages. Selecting a diamond property updates the content of both tabs, here in distribution and here in averages. Let's look at the source and see how it's implemented. In UI.R, we have defined a tab set using tabSetPanel, which will contain each tab. Each tab is created with tabPanel. tabPanel expects the title of the tab as a first argument, and then one or more renderers like plot output or verbatim text output, etc. You can use the command ls to find all the possible output types. Type in ls package :shiny, pattern is output. So we see data table output, HTML output, image output, and so on. Server.r doesn't need any reference to the tabs, and the code looks exactly the same as if there were no tabs. All the communication is done through changes in outputs properties. In this video, we've seen how to use tabs to separate different portions of our interactive web page. This is very useful when building complex dashboards with multiple graphs and textual reports. In the next video, we'll learn how scoping works in Shiny. In this video, we're going to have a look at scoping, that is, knowing where variables can be accessed from. If we want our web page to be rendered efficiently, it is important to know when the code is evaluated, for example, to avoid loading a large file multiple times unnecessarily. The scope of a variable in Shiny is simply defined by where it was declared. Let's have a look at an example. Open RStudio and run shiny, : run app, activity 0702. Open the web page in a different browser or another tab. There are three things to notice. Both pages share the same random value 1. Each user has its own random value 2. And a global variables with the value 42 appears both in the sidebar and the main panel. Let's go through the code and see how this works. In server.r, we see that random value 1 is defined before the call to Shiny server. This will make it available for all users. This is because server.r is run once when you launch the server with run app. Random value 2 is defined inside Shiny server, which makes it only available for each user. This is why the two browsers show different values for random value 2. This is because the function Shiny server is called each time the server serves a new page, so one for each user. Because the code sitting outside Shiny server like random value 1 is evaluated only once when the server starts up, it's a good idea to load large files there for the sake of efficiency. Another way to use global variables is to define them in the file global.r. Like ui.r and server.r, it's a reserved file name used by Shiny. Variables declared there have global scope, but can also be accessed by ui.r, which is not the case for global variables declared in server.r. A global variable is used here in server.r, so it appears on the main panel, and it is used here in ui.r, so it appears in the sidebar as well. In this video, we saw the different levels of scope for variables in Shiny. Slow processes that only needs to be run once, like loading large files, should be put outside the call to Shiny server in server.r, as well as functions that are not reactive, for example helpers and libraries. In the next video, we will see how a user can upload a file to the web page. In this video, we're going to see how to let the user upload their own data for analysis. Suppose you have set up a dashboard with some plots and tables for analyzing your data. How can another user use it for their own data? Shiny makes it very easy to upload a file with a file input function. This function might not work for early versions of Internet Explorer, so use Internet Explorer 10 or any other browser. Let's see how it works. Open RStudio and run the Shiny app activity 0703. Select the file diamondsdata.csv and upload the file. The top panel shows what is known about the file after it's been uploaded. Typically, only the path name is of interest to us in order for us to access it from our script. You can also read the file size in bytes. Files are uploaded on the server in a temporary folder. The second panel shows the first 10 rows of data frame built by parsing the uploaded CSV file. Let's look at the code and see how it's done. In ui.r, we use file input to get the file upload control. It is good practice to specify the type of file you're expecting, text, image, etc. If you're not sure, Shiny will infer it from the file. In server.r, you first need to check whether input file name is null, which is a default value. This will avoid generating errors when trying to process data that isn't there yet. Once the file has been uploaded, downloaded file $datapath contains the location of the file on the server. Output $contents can then access it and read its content. In this video, we saw how a user can easily upload the data and use your plots and reports from the browser without having to use or even know R. In the next video, we'll learn how a user can download a file. In this video, we're going to see how to save data and plots into files from a Shiny app. After having analyzed your data in an interactive web page, it will be useful to be able to save the result in a file. Shiny makes it very easy to download a file using Download Handler. Let's see it in action first. Open RStudio and run the Shiny app activity 0704. Shiny, : run app activity 0704. The app shows the distribution of a random sample. Select the sample size on the left. Clicking on Download as a CSV file creates a CSV file with the raw data and sends it to the browser. Clicking on Download as a PNG creates a PNG image with the data and sends it to the browser. Let's look at the code. The two download buttons are built with Download button. It only requires an ID on a label. In server.r, you need to use the reactive expression download handler to create and export a file. Download handler has two arguments: file name, either a string or a function that returns a string, and content, which is a function with one argument, file, which creates the file you want to export. You don't usually need to specify the file type, text or binary. Shiny infers it from the file extension. This is all you need to enable the user to download a file. Note that we declared the functions random sample and make ggplot object as reactive. Remember that reactive functions save the latest calculated values. Since random sample and make ggplot object are used by a couple of functions, making them reactive prevents them to be recalculated at each call. This is much more efficient. In this video, we saw how it's possible for a user to download results from a web page, either in text file or a binary image file. In the next video, we'll see how to share your Shiny app. In this video, we're going to see how to share your interactive web page with others. So far, your interactive web page has been running on a local server on your machine. You might want to share it with your colleagues or anyone on the internet. Shiny offers a few venues for sharing a Shiny app. Shiny apps can be run either on a dedicated server or locally on the user's machine. With a dedicated server, the user doesn't have to use R. They only need an internet connection and a browser. For this, you have two solutions. You can have your own server. If you have access to a Linux machine, you can install the Shiny server yourself. The advantage is that you have a complete control of the source. The drawback is that it takes some time and expertise to set up and maintain a server. Or you can have an RStudio hosted server. You can open an account on the Shiny server provided by RStudio. The advantage is that it's easy to set up. But the drawback here is that you have to upload your source code to a server you don't control. If you don't use a dedicated server, you can still share your work via the web, but the users will have to run it locally on their machine and from R. In all cases, they can access your code if they want to. Open RStudio and Activity 0705 in the editor. If you use Git for source control software, you can upload your work as a gist or a repository on GitHub. Other users will then use run gist with a number, where the number is the ID of the gist, or run GitHub with the name of the repository and your username on GitHub. Note that the code for these examples are quite old, so ignore the warnings. In both cases, the gist or the repository must contain all the files necessary for Shiny, that is, at least UI.r and server.r. If you don't use GitHub, but can put a file on the internet, for example on your personal website or your personal cloud, as long as it's accessible via a URL, you can simply bundle your work in a zip file and upload it there. Then, your users will use run URL to run it with Shiny : run URL and the URL of the zip file. The files necessary for your app, UI.r, server.r, etc., must be in a subdirectory in the zip file. In this video, we saw a number of ways to share your work with your colleagues or the rest of the world, either by using a dedicated server or by sharing the code in a zip file or on GitHub. In the next section, we will put all we've seen together and build an interactive web page for exploring a dataset. In this section, we're going to use what we've learned so far to build an interactive dashboard with Shiny and ggplot2. In this video, we're going to see what we want the dashboard to look like and what we need to build it. Any data analysis starts with some exploration. With large datasets, it's not practical to generate all possible graphs between variables in advance. Rather, we want to be able to produce graphs on demand. An interactive dashboard allows the user to explore the data quickly and easily. We're going to build a dashboard to produce graphs from a few economic indicators from the World Bank. First, let's see the final result. Open RStudio, make sure you are in the folder section 8, and launch the Shiny app dashboard with Shiny, run app dashboard. The dashboard has two tabs, time series and bubble chart. In the first tab, the user selects an economic indicator and see its evolution through time for 9 countries. For example, CO2 emissions in tons per capita. The user can also plot on log scale if they think it's appropriate. The second tab contains a bubble chart, which shows 3 indicators at once, on the x-axis, on the y-axis, and by the size of the bubble. Each tab has different controls, a drop-down menu and a checkbox for the time series, and 2 drop-down menus and a slider for the bubble chart. To build a dashboard, we're going to need a function that produces a time series plot, a function that produces a bubble chart, and a way to change the user interface depending on which tab is active. The controls are different in the 2 tabs. Based on what we've learned so far, we are set to build an interactive dashboard with Shiny and ggplot2. In the next video, we'll see how to build a time series plot. In this video, we're going to build a Shiny app showing the time series of an economic indicator. As part of our dashboard, we need to build a user interface and a plot for the evolution of some quantities through time. Let's first see what the data looks like. In RStudio, click on Import Dataset and select WDI Data Dashboard.csv. Select the header and click Import. The data is imported and shown in the editing panel. This data frame contains about 20 economic indicators for 9 countries for the period 1960 to 2011. The column names are the codes used by the World Bank database. We'll use the vector code to name to translate a code into something more human-readable. Let's have a look at the code. Open timeseries UI.r, timeseries server.r, and timeseries global.r in the editor. We don't want to present the cryptic column names to the user, so both UI.r and server.r will need to have access to code to name, name to code, it's reverse, to be able to display the full name of the indicators. We therefore store them in global.r. We only need the data to be loaded once, so we put the code for loading the data outside the code to Shiny server. The ggplot contained 2 layers, a geom line for a continuous line, and a geom point for each data point. xlab and ylab set the axis title with the indicator's descriptions. To switch the log scale on, we simply add scale y log10 to the ggplot object p. To see it in action, run Shiny run app time series. The drop-down menu and the y-axis label have descriptive names, and clicking on the log scale toggles the log scale on the y-axis on and off. In this video, we built a time series interface for our dashboard. We saw how to map cryptic column names to more readable descriptions, where to put global variables, and how to add log scale to a plot. In the next video, we'll see how to make bubble charts. In this video, we're going to build a bubble chart in ggplot2 and a Shiny app to use it on our economic dataset. The second tab of our dashboard will contain a bubble chart. There is no bubble chart function in R, but we can easily build one with ggplot2. Open RStudio and run Shiny run app bubble chart. Our bubble chart function will need 4 arguments: the data as a data frame, the name of the column for the x-axis, the name of the column for the y-axis, and the name of the column for the size of the bubble. In essence, we only need to map the size of the geom point to the relevant column. But we can do better and make the plot prettier and more accurate. Open bubblechartserver.r in the editor. Bubblecharт is a function which makes a bare bubble chart with ggplot2. We map the arguments to the aesthetics x and y. We also map radius to the point size. We actually use 2 geom points on top of each other. The first one is colored and a bit transparent. The second one is an empty circle. Shape is 1. The result is a nice looking bubble with a solid outer ring. The points in the legends tend to be very small, so we override them with guides. We add more information to this simple bubble chart later in Shiny Server. The indicator descriptions are used for the axis title and legends. We use scale size area to map the area of the circles to the data and not the radius. This way, doubling the value doubles the size of the circle instead of making it 4 times bigger if we use the radius. In UI.R, we set animate is true in the declaration of the slider to enable the user to see the bubble chart updates over time. In this video, we've seen how to build a bubble chart in ggplot2 with multiple layers, how to customize the legends, and how to make an animation with a slider. In the next video, we'll see how to make conditional panels. In this video, we're going to learn how to dynamically change the user interface in Shiny. Our dashboard will have 2 tabs that each require different controls. We want the interface to change depending on which tab is active. It is possible to hide or show controls on some condition. Let's see an example first. Open RStudio and run Shiny run app conditional. If you select C, a new control appears, from which you can change the value of string 1. Select A or B, and the control disappears. Likewise, if you click on the second tab, a new control appears for string number 2. This is achieved by using conditional panels. Let's see the code. Open conditional UI.R in the editor. The sidebar panel contains 2 conditional panels. The condition for showing or hiding is a string containing some JavaScript, but this is very similar to R. For example, the condition for the first panel is input.someChoice equals C. The value of input$someChoice in R is accessed with input.someChoice in JavaScript, simply replacing the dollar with a dot. When this condition is true, the panel is shown. It is built as usual, with a list of controls on text. To know whether a panel is active or not, we first give a name to the tab set with the argument ID. Each tab in the tab set has a unique identifier specified by the parameter value. If you don't specify the parameter value, it defaults to the title. So to know if the second tab is active, we just need to check whether input $the tabs equals second tab, or, in JavaScript, input.the tabs equals second tab. In this video, we've learned how to make the interface adaptive to the user selection by using conditional panels. In the next section, we'll build our dashboard by integrating the time series plot and the bubble chart in 2 conditional panels. In this video, we're putting everything together and build our dashboard. We have made a Shiny app with the economic indicators time series, another Shiny app with the bubble chart. I know how to change the user interface given which tab is active. We are ready to build our dashboard. Launch R and open dashboard UI.R, dashboard server.R, and dashboard global.R in the editor. Global.R contains the lookup table for translating the indicator code into more descriptive names. As both UI.R and server.R need those, this is the best place to put them. A third vector translates the code to a fuller textual description. UI.R has now the familiar structure: header, sidebar panel, and main panel. The sidebar panel has two conditional panels that appear or disappear depending on which tab is active. Main panel has a tab set with two tab panels, a plot, time series, bubble chart, and a verbatim text, description tab 1, description tab 2. Thanks to the tab set ID, the tabs, we know which tab is active. The tabs are identified with a parameter value, and the conditions are written in a very simple JavaScript. Input.tabs equals first tab, and input.tabs equals second tab. A dot is used instead of a dollar for accessing input$the-tabs. For efficiency's sake, a number of things are set outside Shiny Server. All this code is only run once when the server is launched. The data is loaded. The function bubble chart is defined. This is the code we built in the third video. The function print description is defined. Both functions are used in Shiny Server, but are not reactive, so they are better defined outside Shiny Server. In Shiny Server, we define the four necessary outputs: the rendering of the bubble chart and the time series, with some extra code for customizing the plots, and the rendering of the text boxes with a full description of one or two indicators. Our dashboard is ready. You can launch it and start exploring this real dataset from the World Bank with Shiny Run App Dashboard. Using what we've learned in this course from ggplot2 to Shiny, we built an interactive dashboard for exploring some economic indicators. You are now equipped to build graphs and interactive web pages in R for your own data.